Welcome to this lesson on functions in C. As programs become large, programmers will normally break them down into smaller pieces called functions, each of which performs specific processing. You've already used the printf function throughout many of the programs in this course to display information to the screen. In this lesson, you'll learn to create and use your own functions. Let's go ahead and get started. So you've already used the printf function to display messages such as hello world to the screen display. When our programs run, C starts our programs at main, our main program, or the main function. In this case, main will call printf to display the message hello world. When C encounters that function call, C stops executing the statements in main and goes to printf and executes its statements. When printf finishes, C returns control back to our main program at the statement that follows the function call. In this case, there's no other statements after the printf call, so our program ends. So what do we need to know about functions? Each function will have a unique name. The functions can return a type, such as int, float, or double, depending on the processing they perform, or if they don't return a type, they're said to be type void. A function can receive one or more parameters called arguments. We've already used printf to display integer values, floating point values, character strings, and so the values that we pass to printf are called arguments or parameters. To execute a function, we just simply specify the function's name, parentheses, and any parameters that we're passing to the function. Let's take a look at one. In this case, our program contains two functions. The main function, which we typically have, and then a function called about me. You can see that about me is preceded by the keyword void. That tells the C compiler and other programmers who are reading your code that this function does not return a value. You can also see that we have parentheses following the function name and that it contains the keyword void. That says this function does not get any parameters passed to it. So what does the function do? Within the function, we have our statements within left and right braces. We have three printf statements in this case that display information about me. To call our function within main, we just simply specify the function name, about me. We have to include the parentheses, even though we're not passing any data to the function, to let C know it's a function call. When we run this program, we'll see the following output. So when the program ran, its processing started in main. Our execution is always going to start in the function main. It in turn calls the function about me. At that point in time, C transfers control of the function, executes its statements, then returns back to main at the statement that follows the function call. To better understand this process, I put a couple printf statements before and after the function call. So what should we see? Our program's execution will start in the main function. It'll then display the message, program start in main. It'll call the about me function, which does its processing, and then returns to main, and main will display the final program should end in main. So let's go ahead and run this program. And sure enough, we see that our program execution starts in main. We then call the about me function, which displays its 3 lines of output, and then processing returns to main, where it displays the statement program should end in main. So as you've learned, programs pass data to functions using parameters. You've done this before using the printf function. In this function, or in this main program, we're calling printf with the character string hello. That's a parameter. It's a character string parameter. In the second printf function, we call it with an integer value. So we pass our first function, which has our text and the formatting string. Our second function is the value 50. In the third printf statement, we're passing multiple parameters to the function. Our string that has our format specifiers, the value 50, and the value 100,000. And so when you pass parameters to functions, you separate each parameter with the comma. And then you can just specify the variable name that you want to pass or the value that you want to pass to it. And our function has to be able to receive those parameters. So let's see how a function receives a parameter. In this case, we have a function called say hello. The void that precedes the function name says this function does not return a value, but it does receive a parameter. And so within the parentheses, we specify information about our parameters. In this case, we're going to have a parameter that we'll refer to as count, and it's of type int. Within our function, we're using that parameter value to loop through from 0 to count, displaying the message hello. So if they pass us count of 1, we're going to display hello once. If they pass us count of 2, we'll display hello, hello. And then finally, we display the word world. So let's see how we call the function. So we know that to call the function, we specify the function name with parentheses. And if we want to pass a parameter to it, we include that value within the parentheses. So the first time we're calling say hello, we're passing it the value 1. That should cause the function to say hello world. The second time we're calling it, we're passing the function the parameter 2, which should say hello, hello world. And then the third time, we're passing the parameter 3, which will say hello, hello, hello world. And so when we run this program, we'll see the following output. And sure enough, our code's working. So what do you need to know? For a function to receive a parameter, you have to specify in the parentheses that follow the function definition the variables that will be used to store the parameters. In this case, our function received one parameter, so we have one variable to receive it. We have to specify that variable's type. To call a function using parameters, we just simply specify the parameters within the parentheses that follow the function name. If there's multiple parameters, we separate them with commas. So within our functions, they should perform a specific task. And often to do that, they're going to need their own variables. So in this case, we're declaring a function called max. You can see it gets 3 parameters, each of type int, named a, b, and c. Within the max function, we're going to determine which of those parameter values is the largest. And so we're declaring a local variable, a variable that's known only to the function. So we say its scope is defined to the function. If we tried to refer to that variable max outside of this function, the C compiler would say, I'm confused, I don't know about variable max. So only within the function max is that variable defined. Within our code, we're using some if statements to determine what's the largest value that we've seen so far. We start out by assuming that A is going to be the biggest, so we assign it to max. Then we compare max or B to that value. If B is bigger, it's assigned to max. Then we compare C to that value. If C is bigger, it's assigned to max. And then we return the max value. So you can see, because we're returning a value, up in the top line, we've defined our function as int max. That says it returns an integer value. To call the function, in our main program, we've defined values A, B, C, and D and assigned them the values 1, 2, and 3. Now we know that 3 is the largest value, so that should be the value that gets returned by max. And so we have a printf statement that displays the values A, B, and C, and then calls the function to display which one of them is the largest. When we run this program, we'll see the following output. And sure enough, it says the max of 1, 2, and 3 is 3. So a function returns a value of a specific type, and it receives parameters of specific types. In this case, we have the int max function, which gets the parameters of type int, a, b, and c, and returns an integer value. I've also defined a function called float max. It's getting values of type float. It also uses the parameter names a, b, and c, but because those are associated with the parameters, the local variables of float, they're not confused with the a, b, and c that were used by the int max function. In this case, both functions return the maximum value that they've received. In the int max case, I've used if statements to determine the maximum value. In the float max case, I wanted to show you how you might use the C conditional operator to determine the max. You should spend some time with that code to see how it's determining the maximum value. Within main, we declare variables of type int and float. so we can call both functions. And so you can see that we're displaying the values that we're passing to the functions using printf, and then we're calling the corresponding functions. And so to call our max function, we use the name max. To call our float max function, we use the name float max. Let's go ahead and run this. And sure enough, we see that the larger of 1, 2, and 3 is 3. The larger of 1.1, 3.3, and 2.2 is 3.3. So our functions are working. But what you need to know, or what you should take from this, is our functions get parameters of specific types. Our functions return values of specific types. And so in this case, we had two functions that performed similar processing. They both returned the max value. But because they use different data types, we had to create different functions. So in C programs, main is a function. It's also the first function to execute, so it's kind of our main program. But we've declared it as int main void. And we've said that the int says that's because main can return an integer value to the operating system. The void that follows the main says we're not using command line arguments for this program. And so in the first case, we're just calling printf, and we're displaying our hello world message, and we're not returning a value. We really should when we define main as type int. So in the second program, we return the value 1, saying that we're successful. And so when we run this program, we'll see our output. Our compiler in this case included code that says, hey, you exited the program with a status value of 1. And so the point of this is functions can return a value, and main is a function, so it can return a value, in this case, to the operating system. If your main function doesn't return a value, you should typically declare it as void main void. That tells the C compiler that we're not returning a value, also tells other programmers that you're not returning a value. So as you examine C code, you're going to see main defined in a variety of ways. But typically you'll either see int main void or void main void. But when main returns a value, it's returning it to the operating system. If we had run the program from within a script, we could look at that value, and our script could perform conditional processing, responding to whether or not our program was successful or encountered an error. And so main is a function, and you've learned that you can pass parameters to a function, and main is no different. When you execute a command from the command line, in this case copy filename.txt to filename.back, the command name and the parameters you pass become command line arguments. The operating system passes those arguments to our C program by passing parameters to main. The first parameter, int argc, is a count of the number of command line arguments. The second parameter, char asterisk argv brackets, is an array of character string pointers that point to the actual command line arguments. So let's go ahead and run this program. And we see that the program loops through the command line arguments. Now in this case, in this environment that I'm running, I didn't pass command line arguments to it, but by default, the program name will always get passed to argv. And so our program displays the arg count value, 1. It got passed one command line argument, the program name, and then it looped through argv to display the command line arguments, in this case, just the program executable name. Now we've got a lesson that examines command line processing in detail, but as you look at C programs, you're going to see main receiving parameters. Those parameters correspond to the command line arguments. So as we create functions, one of the things that we should keep in the back of our mind is, ideally, our function should have only one return statement. That way we know our functions start at the top and they end at the bottom. But our first function here, int compare, is comparing two values. If they're equal, it returns the value 0. If the first parameter is greater than the second, it returns the value 1, and otherwise it returns the value 2, meaning the second parameter was larger. And so if we call this function within main, we see that we're comparing 33 and 22 yields 1, which means the first parameter was larger. What I don't like about this function is that it has multiple return statements. And ideally, our functions should have one return statement. So let's take a look at an implementation that does just that. In this case, we're declaring a variable called result. And if a is equal to b, I'm saying result is equal to 0. If a is greater than b, result is equal to 1. Otherwise, result is equal to 2. Then I have one return statement down at the bottom of my function that returns the value of result. And so if we run this program, we see that we get the same results as the previous function, but we've done so using a function that uses only one return statement. And there's going to be times where you can produce readable code using multiple return statements. But ideally, in the back of your mind, just keep the fact that I should only have one return statement in my functions. When you use functions in your programs, the C compiler needs to know about the function before you can use it. And so in this case, we have our header file, standard.io.h. We then have our main function. And you can see that it's calling the function compare to compare the values 33 and 22. And then the compare function is defined right after that. So there's our function. We know how it does its processing. But when we run this program, we get a syntax error. And the compiler says, I don't know about the function compare. Now if we look at our source code, compare is right there. The problem is, the definition of compare is coming after the first time we try to use it. Now we could solve this by moving compare above main, just cutting and pasting it, and then this program would compile and run, and everything would be good. But sometimes we'll have our programs that are so large, they're in multiple files, and we'll need to include those files. And we don't always know if we're going to get them in an order that the C compiler will like. So something that C programmers use is a function prototype. And a function prototype is just kind of a copy of the function declaration's first line. And so in this case, we're using a function prototype for compare. It says, compare is a function that returns the type int. It gets two parameters. They're both type int. And then we have the semicolon. The function prototype says, I'm going to be using a function called compare. I'm not defining it now, I'm defining it somewhere else. But you need to know about it so you don't give me a syntax error. And so when we compile this program, because we use the function prototype, our program compiles successfully and runs. So a lot of our header files will include function prototypes. And so if you search your compiler's files and look at the different header files, you'll encounter a lot of function prototypes. But that's the purpose. It's just to help us define to the C compiler or describe to the C compiler a function that's defined somewhere else, but that we're going to be using. So you've learned that when the C program calls a function, execution stops in the main program and branches to the function where its statements execute. And now we can pass parameters, arguments, to the functions to perform their processing. But to do that, the C compiler behind the scenes has to put in code that says, I'm calling a function, so I need to save the location that I'm currently at so I can come back to it and continue my execution. The C compiler also has to provide a data storage place for the parameter values that's passing to the function. It does that by placing the data on a special data structure behind the scenes called the stack. And so when we call a function, it'll first save the return location. It'll then put each one of the parameters on the stack, and all that adds a little bit of overhead. Now normally it's fine, programs are fast, CPUs are fast, and it doesn't impact us. But let's take an example of just how much overhead can happen. We're declaring a function of type float called add. It just adds them up. It gets two parameters, a long int a and a float b. And it's adding them and returning the result. And so we've got a function, it's just going to add two values and return a result. And so we're going to call it from main. And so we're going to keep track of how long that takes to execute the functions. And so our program starts out and we display a message say we're calculating the time. And then we go out and get the current system time. And then we're going to call the function atom, and we're going to also do a similar processing within a for loop that adds the values. We're going to compare, if I just did it in line, how does it compare time-wise to calling the function? So our program first loops. You can see we're using a long int, and we're looping through a billion times to see how long it takes to add up a billion numbers. And then we're going to display the result in seconds. Then we're going to do similar processing, adding up a billion numbers, but by calling our function. And so let's take a look. Let's go ahead and run this. So we're calculating a billion numbers. It took 2 seconds. But using the function, it's still calculating. It took 7 seconds. So we did similar processing. We added a billion numbers. But the second time, we did it by calling a function. And we learned that every time we call a function, there's a little bit of overhead. And so in this case, it took a billion calls to see that overhead because things are so fast. But I just want you to know that functions improve the readability of our code. They allow us to reuse code because a function we create for one program, we can probably use in another. But every time we call a function, there's a little bit of overhead. And depending on the processing your program must perform, there may be times where you'll say, I'm better off not to use a function just to make things faster. So we've learned that when a function defines a variable, that variable is known only to the function. Programmers will say that variable is local to the function. Sometimes, depending on the processing our program performs, we want to have variables that are known everywhere. And they're called global variables because the C compiler can use them in every function that we create. And so in this case, we're creating global variables. They're defined outside of any function, A, B, and C. Then we have our function definitions. A function called initialize that doesn't return a value, doesn't gain parameters, but you can see it's using the global variables A, B, and C. We have our main, which calls that function initialize to initialize those global variable values. And so let's go ahead and run this. And we can see, sure enough, the global variables were initialized to A, B, and C. Now, global variables can be convenient, but they also can lead to errors that are difficult to debug, and they can cause code that's more difficult to read. And so typically we avoid them. But if you see variables defined outside of a function, then you know that they're global variables, and you can just use them anywhere, kind of however you want. That's part of the problem with global variables. Someone else writes a function that uses them, and it may change their values, and you didn't ever see that happen in your code as you're reading through it. So you want to try to avoid the use of global variables, but you may see them defined as you look at other C programs. And so a global variable is known throughout your entire program. In contrast, the variables that we declare within a function are known only within that function. And we'll see how that works here in a second. So when your program uses global variables, and ideally it doesn't, and your program has a function that declares local variables, there may be times when the names conflict. So if we look at this program, we've got global variables A, B, and C, and we've initialized them to 1,000, 2,000, 3,000. We know they're global because they're declared outside of any function. Then we have a function that's called hasConflict. It also declares variables A, B, and C. And so we've got variables defined with the same name. What C does, when a function defines variables, then it will create those variables within the function, but they'll only be known to the function. And so in this case, the function initializes A to 1, B to 2, C to 3. And those are our local variables. It has nothing to do with the global variables A, B, and C that have the values 1,000, 2,000, and 3,000. Those are different variables. And so when we call our function, let's take a look at this processing. So when the function hasConflict, it shows that the variables A, B, and C have the values 1, 2, and 3. It should, they're local variables. But in main, the variables a, b, and c have the values 1,000, 2,000, 3,000. And so hopefully, just this example alone said, this can get confusing. And so, first of all, it didn't help us, our variables didn't have very meaningful names, just a, b, and c. But then the use of global variables can add to conflicts, and you'll start to think, am I talking about the global variable here, or am I talking about a local variable? That's part of the problem. And so we should try to stick to local variables whenever we can, and we'll eliminate this confusion. So you've learned that you can pass parameter values to a function, and when you do, the C compiler will assign the parameters to the local variables within the function. And so let's take a look at what that means to our programs. We've got a function, and it's called change values. It doesn't return a value, but it gets two parameters, one of A of type int and B of type int. Within the function, it assigns A the value 1,000 and B the value 2,000. Within main, we're declaring variables A and B, and we're calling the function change values, and we then display what those ending values are. Let's run this program and see what happens. And so our program starts its execution in main and initializes the variables A and B to 1 and 2. We then call the function change values, passing the variables A and B to the function. Within the function, it assigns A and B the values 1,000 and 2,000. But when our program gets back and we look at the ending values, they've not changed. They're still 1 and 2. And that's because C uses something called call by value. When we call a function and pass parameters to it, C will make a copy of our parameter's current values and put it on the stack. In this case, when we call change values with A and B, C will place copies of the values 1 and 2 on the stack. And so the values that the change values function gets is 1 and 2. It doesn't know about our variables A and B. To change a variable's value within a function, we have to pass the memory locations of those variables that we want to change. That's where pointers come into play. And C programmers who are just learning C will say, pointers, I'm so confused. And so what we need to pass in order for it to change the values of the variables A and B is the memory addresses of those variables, so our function has a copy of those memory locations and can change them. So what you need to understand is if you pass a parameter to a function, you can't change that parameter's value unless you use a pointer, and we'll see how to do that. So we just learned that when we pass a variable to a function as a parameter, we can't change that variable's value within the function unless we use a pointer. So we've modified our function change values to receive a pointer to a variable of type int and a second pointer to a variable of type int. That means they're going to get the address locations of the variables that we want to change, so it can use pointers to change their values. So in this case, the code says, assign the value that's pointed to by A, the value 1,000, and assign the value that's pointed to by B, the value 2,000. So how does our calling sequence change within main? In main, we declare the variables A and B. We assign them to value 1 and value 2. That's pretty straightforward. Then we call our function. Because we want to change the value of a parameter, we need to pass our variables by address. So we use C's address operator, that ampersand. And so we pass ampersand A, the value of our variable A, and ampersand B, the value of the memory location of our variable B. And so we're passing pointers to the locations in memory, so our functions can change the values of those locations in memory. So when we run this program, we see that our ending values for the variables are indeed 1,000 and 2,000. The way we got there was to use pointers. So anytime you want to change the value of a variable within a function, you have to use pointers. And we have a lesson that's on pointers, so you'll start to understand pointers in detail. But you'll just need to know that I need to use the ampersand operator to pass the address of my variable so the function can change it. Otherwise, C will use call by value and just put a copy of the variable's value on the stack. And then our functions have no way of changing the variable's value because it doesn't know where the variables are in memory. Let's look at another example. We have a function that's called swap values. And its whole purpose is to get one value of type float and a second value of type float and swap their values. And so you can see that it's receiving a pointer to a function of type float and a second pointer to a function of type float, meaning it's getting the locations in memory of a value of type float and the other location in memory of a value of type float. Within our function code, we create a variable called temp so we can store the value that's pointed to by A temporarily so we don't lose it when we assign A the value that's pointed to by B. And so we kind of do a three-step swap to swap the values. And so within main, we create a variable called big and assign it the value 1000, and we create a variable called little and assign it the value 0. Our goal is to swap the values. So we call our swap values function, but to change a variable's value within a function, you have to pass the variable by address. So we precede the variable name with the ampersand. We do that for both big and little. And so when we get back from the function, let's run our program. We see that big now has the value 0 and little now has the value 1000. So we've swapped the values as desired. So anytime you want to change the value of a variable within a function, you have to use pointers. And we'll have a lesson on pointers within this course. And so you've learned that an array is a data type that allows us to store multiple values of the same type. And so you've also learned that to change a parameter's value within a function, you have to pass the address of the value that you want to change. It turns out that when you pass an array to a function, C will pass the array's address. So in this case, we have a function called showArray. It's receiving an integer array. It doesn't say how big it is, but we get a second parameter that specifies the number of elements. And within the function, we just loop through the elements of the array, displaying their value. Within main, we define our array values and assign it the values 10, 20, 30, 40, and 50. And we call the function specifying the array name and the number of elements. When we run this program, sure enough, we see our array values 10, 20, 30, 40, and 50. But the point to note is we didn't have to use the ampersand character because when we use arrays, by default, C will pass the address to the array. Let's look at another example. We have a function called string to uppercase, and it's receiving an array of type char. Within the function, it's looping through each character of the array, converting the character to uppercase. Within main, we define the array, string, we assign it to values A, B, C, D, E, F in lowercase, and then we call the function, passing to the function our character string. Now our function knows where the last character in the string is because it's pointed to by the null character. So we loop through A, B, C, D, E, F, we encounter the null, and it ends. And so when we run this program, sure enough, we see that it's successfully converted everything to uppercase. Normally when a function runs, it performs its processing, ends, and its local variables were on the stack and they just get discarded. And so a function can't remember the previous values that it had. It gets a new copy each time it runs, and then those get discarded. There may be times, however, where it'd be nice for a function to be able to remember something about its previous processing. To do so, we can use something called a static variable. And so in this case, within our function, it's called total characters. It receives an array of characters. It's going to count the number of characters in the array. But it's going to use a variable called count that's static to remember how many variables or how many characters have I seen so far since every time I've been called. So I got called once with a string that was 5, so I saw 5 characters. Then I got called with a string that was 10, so I've seen 15 characters. So it's going to keep a track of the number of variables it's seen. Let's go ahead and run this and get an idea of how it does its processing. So the characters counted so far, it got past the string A, B, C, D, E, F. There's 6 characters, so it counted them. It gets past 6 more. So it's, as I've seen, 12 so far. Then it's seen 6 more, 18, and finally it sees all the letters of the alphabet. And so you may encounter, as you look at C programs, variables defined as static. That just says they should exist after the function ends, and so we can go back and use their value. They're not very common, and they can lead to errors that are difficult to debug, but because you'll see them, I wanted to present them here. As you examine C programs and different functions, you'll periodically see the const, C-O-N-S-T keyword. And that tells the C compiler that the variable we're creating is a constant. And so we've learned that we can define constants using macros, but in this case we want to be able to use a variable of a specific type, and we want to initialize it, but then after that it shouldn't change. And so we've done that here with the variable I, but then we try and use I again to control our loop, and we try to initialize I to 0. Well, we've said I is a constant, it shouldn't change. So when we run this program, the C compiler says, whoa, wait a minute, you're trying to change a variable that you told me is a constant. Now where you'll see the const keyword is in a lot of function definitions, it will define parameters as a constant so you know that their values don't change. But when you see the C-O-N-S-T keyword, the const keyword, just know that you're telling the compiler once this variable has its value, it shouldn't change. If I try to change it, display an error message. So in most cases, we call a function, it performs its processing, and it returns. We say our functions should perform a specific task. Well, a fun process is to create a function that calls itself until an ending condition occurs to perform a task. And several things are kind of defined in terms of themselves. And so let's understand the factorial. And so a factorial of 1 by definition is 1. But the factorial 2 is defined as 2 times the factorial 1, or 2 times 1, so 2. The factorial 3 is defined as 3 times the factorial 2, which is defined as 2 times the factorial 1. So each one of our definitions is based on kind of the previous factorial until we have the ending condition of a factorial 1. And so recursion is the process of a function calling itself. And this is a pretty advanced topic, but in general, if you hear the term recursion, you're just going to know, okay, the function calls itself to perform a specific task until an ending condition is met. Let's take a look at our factorial example. In this case, we have a function called factorial. What do we know? It returns a value of type int. It gets a parameter of type int. Within the function, we look at the parameter value. If it's 1, we return the value 1. That's because the factorial 1 by definition is 1. But if it's another value, then we return that value times the previous factorial. So we're taking, if we get the value 3, we would take 3 times the factorial of 2. If factorial 2, we'd take 2 times factorial 1. And so the function is going to continue to call itself to perform its processing. Ultimately, we'll get to the factorial 1, which returns 1. That will return 1 to the factorial 2, which will return 2. That will return 2 to the factorial 3, which returns 6, and we work our way back out. So our main program is calling the factorial with the values 1 through 5, so we can see the processing. Let's go ahead and run this. And so it tells us the value of factorial 1 is 1, that's right, of 2 is 2, of 3 is 6, of 4 is 24. So it's processing correctly. But we're using a recursive function, a function that calls itself to perform the processing. Let's add some printf statements so it's easier to understand what's going on. In this case, within our factorial function, we first say, hey, I'm in the factorial with a value of something. And then if the factorial is 1, it says, I'm returning the value 1 back. So otherwise it says, I'm going to call current factorial value times the factorial of n minus 1. So let's go ahead and run this. And so we first get called with the factorial value of 4. So it says I'm going to return the value of 4 times the factorial of 3. So we're in the factorial with the value of 3. It says I'm going to return 3 times the factorial of 2. We're in the factorial with the value 2. It says I'm going to return 2 times the factorial of 1. It says I'm in factorial with the value of 1. I'm going to return 1. So it returns 1. That gets multiplied by 2. That gets multiplied by 3. That gets multiplied by 4. We get our ending result. Let's take a look at another example. We've got a function that's called display in reverse. And our goal is to take a character string, such as hello world, and display it in reverse order. We're going to do that using a recursive function, a function that calls itself. So let's take a look at our code that we're performing within display in reverse. It says, is the character I received null? Marks the end of the string. If it's not, call display in reverse with the next character. And then when I get back from that, output my character. And so let's run this. And sure enough, we get our string called in reverse. So when we have a factorial definition, or we're creating a factorial function, we need to have an ending condition. In the case of factorial of 1, that was defined as 1, so we can stop calling ourselves and start returning values back up. In the case of our display in reverse, when we get to the null character, we found the last character in the string, so start returning back up the chain. And so this is common to factorial functions. We'll see factorials in some of our dynamic data structures that we look at in later lessons. And so recursion is fun. Creating a function that calls itself is kind of cool. But because it's lots of function calls, there's also lots of overhead. And so your recursive functions are great if you can produce code that's just nice and concise and easy to read and understand. In this case, we have a recursive function called string length. Or I guess we have an iterative function called string length. And it's just going to loop through and count the number of characters in a string. And so we can take a look at our processing time for that. Let's go ahead and run this. And so we're going to count the strings a various number of times, and it took our processing time 2 seconds. And so we counted the string, looks like 1 billion times. And so our CPUs are fast. Now we've got a recursive implementation of the string length function. So it looks to see if the string is currently pointing to at null, and if it isn't, it calls itself with the next character in the string. And it calls itself until we get to an ending condition where it's null, it returns 0, and that returns back to 1, 2, 3 backwards. And so we've got a recursive implementation of string length. Let's go ahead and run this and see how long it takes. Previous one took 2 seconds. And this one took double the amount of time. So as you're trying to make your determination, should I do something recursively or not, keep processing overhead in mind. But also, if you can create something that's recursive and is easy to understand and read, then that's great. That's when you should use recursion. So far, all of our functions that support a number of parameters have supported a fixed number of parameters. That's normally the case. But you've seen the function printf, and you can pass any number of parameters to printf. And so it's just implemented differently. And so I'm going to include, it's an advanced topic, but I'm going to include the source code out on the lesson file that allows us to create a function that supports a varying number of parameters. This is not common, but there are cases like printf where it becomes, increases your function's processing capabilities. And so we're going to create a function called add values. And it's capable of adding 2 values, 3 values, 4 values, 5 values. So it supports a variable number of parameters. And to do so, it uses a process called a variable argument list. And so again, I'm just going to run this so you can see it. But I'm going to leave the code for kind of your self-study because it's too advanced to talk about here. But you can see that we called the function with a variety of different number of parameters, and it summed them up just as it should. And in a similar way, there may be times where we want to support a varying number of parameters that differ by type. And I'm including a program out in the class files that has the same capability. But you'll see it operates very much like printf, that you can specify a format specifier, such as %d, to say, hey, this is an integer, or %f to say this is a float. And so, again, I've got the code out there for you, but we won't drill into it here. And so what are you going to learn next? To save C programmers time, C compilers provide a library of built-in functions that your programs can call. For example, there's the abs function that returns the absolute value of a value that's passed to it. In the next lesson, we're going to take a look at the C standard library, several of its routines that you can make immediate use of within your programs.